before going into the statistical characteristics of turbulence, we will try to understand that what are the instrumentalists who play a big role in sustaining and creating the turbulence. And to do that, we will look into the characteristics of these creatures known as eddies. So, what are these? These are basically lumps of fluids or strongly rotating structures, and how big or how small these are, this is a very interesting question, because the largest eddies may be as big as that of a system and the smallest eddies may be as small as the molecular dimensions or close to that. If not exactly the molecular dimensions, that may be an exaggeration, but it may be very close to very small length scale. So, that we understand that when we mention that there is a wide range of length scales, we are talking about like some mechanisms or some media through which the turbulence is participating, it is having its activity, and that is through such eddies which are of widely varying length scales. So, what is happening with these eddies? To understand that, what we will do is we will say that if you have a velocity of the flow, if we somehow try to write it in terms of some average velocity plus some fluctuation over the average velocity. So, this is mean. We will see mean is again not a complete definition, because what sort of mean, what sort of average, that we will see that when you go to the statistics of turbulence, there are many ways in which you may do an averaging, but right now, so we are going from a more qualitative field to a more quantitative field. So, right now we just consider it as some kind of averaging. What kind of averaging we will see, and important thing is that over and above that average there is some random fluctuation. So, where from this random fluctuation is there, these are there because you have some disturbance in the flow. So, the disturbance in the flow may be instigated by the roughness elements of the wall, or maybe slight changes in the inlet conditions of flow through a pipe or a tube, and that is how this fluctuation is there. So, when this fluctuation is there, then what happens? First of all, these fluctuations create a rotating structure or structures of rotating elements of different length scales in the flow, and such rotating elements are called as eddies. So, when you have the largest eddy, so the largest eddy has a length scale which is of the length scale of the system. So, in the largest eddy scale, what is happening? The mean flow has some kinetic energy. So, the large eddy, what it does? So, large eddy extracts some kinetic energy from the mean flow. So, when it extracts some kinetic energy from the mean flow, then what is happening? Now, the large eddy has some activity, it has sort of like a rotational kinetic energy, and then with that activity it might get evolved into smaller eddies. So, the next step is that the large eddy, or we should say the largest eddy, because large is again a comparable term. So, largest, the whatever is the largest in the system, and the largest eddy we should keep in mind that it is of the order of the system length scale. Then the large eddy, these large eddies, such large eddies, what they are doing? They are getting evolved into smaller eddies. So, the smaller eddies which are, so therefore in a system you have large eddy and then smaller eddy and smaller eddy, but there are important characteristic differences between the large eddy and the small eddies. What are these? The large eddy has the order of its dimension as that of the system length scale. So, if the flow over the system length scale is such that the flow is of high Reynolds number, that means with respect to the length scale of the large eddy, let us call that some length L. With respect to this length scale of the large eddy, the Reynolds number is high. If with respect to the system length scale the Reynolds number is high, and we have seen that the turbulent flow has characteristic that it is for a high Reynolds number. So, the Reynolds number is high, and when the Reynolds number is high, that means for the large eddy inertia forces dominate over viscous forces. So, much more significantly dominate, not just dominate, much more. So, if the Reynolds number is say 10,000, that means roughly that 10,000 times more becomes the inertia force. So, for the large eddies, these eddies, you have the Reynolds number based on the eddy length scale is very large, which means the inertia forces much more significantly dominate than the viscous forces. Now, large eddies evolve into smaller eddies and energy is transferred or extracted from the large eddy to the smaller eddies. So, there is a transfer of energy. First the energy, so if you look for the transfer of energy, first there was a mean flow, we are basically talking about kinetic energy. So, from mean flow to large eddies, then to smaller eddies. So, this is how energy is being transferred from large eddies, and the large eddies evolve into smaller eddies. So, you have the transfer of energy, and these evolve into further smaller eddies. So, again the energy is transferred like that. So, this is known as cascading of energy. This phenomenon is known as energy cascading. What is important is that what happens at the end, what is the smallest length scale that we are looking for, that is where will this energy cascading stop, what will be the smallest eddy size, because that will give us an idea of the range of length scales that we are having. So, in this way the energy will finally reach the smallest eddies. What are the characteristics of the smallest eddies? See, as you are reducing the sizes of the eddies which are of your concern, you see the large eddies have the largest characteristic length scales, but if you go to smaller and smaller eddies, the length scales of those eddies are smaller and smaller. That means the Reynolds number based on the length scale of the eddy becomes smaller and smaller. See, we are talking about the length scale of the medium through which the turbulence is being generated and sustained, and that is the eddy. So, that is of widely varying length scale, because the largest one is of system length scale, but you also have smaller and smaller eddies, and in this way you will come down to situations where now the viscous forces are tending to get more and more important, because the Reynolds number based on the length scale of the eddies is getting progressively smaller as we are thinking of smaller and smaller eddies. So, where we will stop, we will come to a stage when you have smallest eddies, and in the scale of the smallest eddies you have viscous forces at least equally important than the inertia as compared to the inertia forces. That means when we talk about the smallest eddies, we talk about a case when the Reynolds number is of the order of 1, that is a limiting case. Why it is a limiting case? Because now viscous forces will take over, and when the viscous forces will take over, whatever energy that has been extracted from the mean flow by the largest eddies and it has been cascaded to the smallest eddies, that will be dissipated through viscous diffusion. So, the energy extracted from the mean flow comes to the smallest eddies, and these dissipate the cascaded energy through viscous dissipation. Since the length scales of the large and the small eddies are different, to exemplify that we will consider that the smallest eddy length scale we will give it a different name. So, we will call it eta. So, eta is different from L. L is the largest eddy length scale and eta is the smallest steady length scale, and let us try to develop a sort of qualitative understanding of these length scales. So to do that, let us try to figure out that what is the kinetic energy that is extracted from the mean flow and what is the dissipation of kinetic energy that is there through the smallest eddies by this energy cascading mechanism. So to do that, we understand that if you have the rate of extraction of kinetic energy from the mean flow, this is through the fluctuation. So if we know what is the characteristic velocity scale for the fluctuation, let us say that u is the or u naught is the characteristic velocity scale for fluctuation in the largest scale. So there is a whole lot of fluctuation, and because of this fluctuation you have the kinetic energy extracted from the mean flow by the largest eddies. So largest eddies are getting energized because these fluctuations are getting amplified. In a turbulent flow such eddies cannot be sustained, in a laminar flow such eddies cannot be sustained because these perturbations or fluctuations cannot get amplified. So you cannot have, so eddies can sustain only when they have sufficient energy because they are rotating lumps of fluid, so to say. So there must be something which helps them in sustaining their motion, and that is extraction. The key is in the large scale it should be able to extract kinetic energy from the mean flow, and that is only by the fluctuations. So if you have fluctuations dying down, then that is not possible. Therefore you can't have eddies in a laminar flow. Now if you find out the rate of extraction of kinetic energy from the mean flow, then what is happening in this, basically you are writing the kinetic energy per unit time. So kinetic energy is like if you write it in terms of per unit mass. So let us write everything per unit mass. So we are not mentioning it explicitly. So it is just like half mv square. So per unit mass, if you write it is just like half v squared, but that half is not important for us, we are just writing the order. So it is just like say u0 square divided by the time. This time in the large range, in the large eddy scale, is known as turnover time. What is this turnover time? This is a time that is necessary for the large eddy to be energized by extracting energy from the mean flow. So what is the time that it takes? Characteristic time scale that it takes to be energized by extracting the energy from the mean flow, and that will depend on the velocity of the flow. So that we can write as L by u naught. I mean always when we are writing this, these are, we should give a better symbol as this one tilde, which is meaning the scale. That means it is not that t is exactly equal to L by u0, but order of magnitude of that is dictated by the length scale and the velocity scale at that condition. So that means, so if you give it a name as say pi, so this is per unit mass we have to understand. So pi is of the order of u0 cube by L, that is the rate of extraction of kinetic energy from the mean flow. So let us write the scales. So let us say that you have a mean flow and or let us say we have a large eddy and a largest and smallest eddy. So largest eddy and smallest eddy. So the length scale of the largest eddy is L, the velocity scale is u naught, and the time scale is t. So we will have some scales for the smallest eddy also, and our objective will be to compare these scales to see what is the total range of scales over which the activity is going on. So for the smallest eddy we have, let us say eta, that is the symbol that we have given as the length scale. Let us say v is the velocity scale and maybe say t prime is the time scale, just some names. So in the smallest steady scale what is happening, there is a viscous diffusion that is taking place. So whatever is the kinetic energy that has been extracted and being transmitted to the smaller eddies, the smallest eddies, that it is now dissipating through viscous mechanism to its surrounding fluids. So entire energy, so it is not able to sustain its rotationality anymore by going to smaller scales, because it is dissipating entire energy because of the dominance of the viscous force. Now the dissipating mechanism is very strong. So the rate of dissipation is something what is important, rate of dissipation at the smallest steady scale. So what is the rate of dissipation at the smallest steady scale? So if you have, say, let us call it epsilon. So the rate of dissipation is given by, like if you again write it as per unit mass, it is given by 2 into nu into the rate of deformation. If you call it Sij as the rate of deformation, then Sij is like half of del uy del xj plus del uj del xi, that is the rate of deformation. And the rate of dissipation at the smallest steady scale is, I mean this is not just for smallest steady scale but any scale, but here we are talking about the rate of dissipation. So the rate of dissipation at the smallest steady scale will also be governed by this rule, only the velocity and length scale we have to identify properly. So what is that? So 2, again the factor 2 we forget, we just write nu, which is the nu is the mu by rho, the kinematic viscosity. So nu into the rate of deformation square, basically into the rate of deformation square. So the rate of deformation is what? Rate of deformation is some velocity by its length scale. So velocity is v and length scale is eta for the smallest eddy. So nu v square by eta square, order of magnitude. That is one of the important things. The other important constant is that over the smallest eddy length scale, the Reynolds number should be of the order of 1. So the third constant, so let us just keep these scaling expressions in mind, that in the smallest eddy length scale you have the Reynolds number with respect to the length scale eta is of the order of 1. That means v into eta by nu, that is equal to 1 or of the order of 1 again. So this length scale you may write in terms of this epsilon, the rate of dissipation at the smallest scale. So it is possible to write v is of the order of nu by eta, and therefore you have epsilon is of the order of nu into v square by eta square, that is nu into nu square by eta square, that means nu cube by eta square. That means what is eta? Eta is of the order of nu cube by epsilon to the power or to the power, yeah, sorry. So v is of the order of nu by eta, so again it, sorry, this will be v to the power 4, right. So nu into v square by eta square, that means nu into, so let us just write it bit properly. So epsilon is of the order of nu into v square, sorry, yes, v square is nu square by eta square and divided by another eta square, so nu cube by eta to the power 4. So this will be nu cube by epsilon to the power 1/4, right. So when it is nu cube by epsilon to the power 1/4, so as if you know what is epsilon, you know what is this eta, the smallest scale, but this is not complete because you say that we do not know what is epsilon. So to know what is epsilon or to estimate what is epsilon, we will go through maybe one simple step, but it is important to understand that if we know epsilon, this gives the length scale of the smallest eddy, and that is known as Kolmogorov length scale. Kolmogorov length scale or micro scale. So how do you estimate the Kolmogorov length scale? That is quite straightforward, because at the end you must have whatever energy that has been extracted with a certain rate from the mean flow, the energy at the same rate has got dissipated from the smallest eddies, otherwise there will be accumulation of energy at the intermediate eddy scales, and that will disturb the structure of this energy cascading. So you must have the order of pi same as the order of epsilon. So whatever is the rate at which the energy has been extracted from the mean flow, that has been the same rate at which the energy is dissipated. So that means you have u0 cube by L of the order of epsilon, right. So you can write epsilon from the characteristics of the system. So that means you can now write the eta as of the order of nu cube by epsilon is like u naught cube by L to the power of 1/4. So what it means is now you can write this eta. So let us take a fourth power of all the sides. So you have eta to the power 4 is of the order of nu cube into L by u naught cube, right. So if you simplify it one more step, if you write eta by L, that is if you divide by L to the power 4, so what it will bring rise to, okay. So this is nothing but 1 by Reynolds number with respect to the system scale cube. So eta is of the order of L into Reynolds number to the power minus 3/4. This Reynolds, so we are relating the smallest eddy length scale with the system scales. So let us stop for this lecture now, and the next lecture we will see that what are the approximate magnitudes through some practical numbers, that what are the approximate magnitudes of these length scales and the velocity scales. Okay.